Lesson 3.7, Day 2. We're starting off with the derivative of inverse trig functions. I'm going to develop with you where the inverse sines derivative is coming from, and then we'll give you the rest that you can either derive yourself or commit to memory. To solve for the derivative here, I'm going to first rewrite it so that it's not an inverse trig function. I'm going to flip it around to say the sine of y is equal to x. What that means graphically is that you have an angle of y, and the sine of that angle is x. Opposite divided by hypotenuse would be the sine. Then we'll take the derivative. Derivative of sine is cosine. Cosine of y, but I'm solving for dy dx, differentiating with respect to x. So that means by the chain rule, I have to then say the derivative of y with respect to x, as we did in implicit differentiation, is equal to, now I have an x, so its derivative is 1. dy dx is equal to 1 divided by the cosine of y. If I go to my picture, cosine would be adjacent over hypotenuse. I can find the adjacent with the Pythagorean theorem. It would be 1 minus x squared being divided by a 1. So the end answer for the derivative of the inverse sine is 1 over square root of 1 minus x squared. Oops. Here's the list of all the inverse trig derivatives, and you have that list. You can see we just created this one. All of these are in terms of x, so just be aware that when we go to do some, we're going to have to use the chain rule because my input is more than just x. So you're going to end up with times the derivative of the inside by the chain rule. Y prime equals, first derivative of inverse cosine, negative 1 over square root of 1 minus, and then our input is 1 over x, and it's being squared, times the derivative of our input, because this is not just x, this is a function of x. Think of it as x to the negative 1. Its derivative is negative 1x to the negative 2. In the simplification process, the negatives go to positive 1. The x squared goes to the denominator, and we have a complex fraction. So this is one possible answer, but chances are, if you saw it as a multiple choice, there's a couple other contenders that we want to talk about. One of the things that you can do to simplify, to not have this be a complex fraction, is to bring the x squared inside the square root. To bring something inside, you need to square it. 1 over the square root of x to the 4th times 1 minus 1 over x squared. That turns into 1 over the square root of x to the 4th minus x squared upon distributing. This is one possible answer, and it's not a complex fraction. You could also have another equivalent answer. X squared is a common factor. Let's pull x squared out. 1 over square root of x squared is absolute value of x times x squared minus 1. Inverse tan of 2x. Its derivative, inverse tan is done first. 1 over 1 plus our inside quantity is being squared according to inverse tan's formula, times the derivative of the inside, which is 2. Simplification leaves us with 2 over 1 plus 4x squared. The last problem is a composition of 3. We have the square root, which is something to a 1/2 power. Inside, arc sine means the same thing as inverse sine, and it's of 9x squared, which is a quadratic. Derivative is outside done first. 1/2 goes in front. Keep the inside the same. Finish off the power rule. times the derivative of the first one inside of that composition, 1 over square root of 1 minus our input squared, times, finally, the last piece, its derivative. Simplifying to condense this answer, 18x times a half gives me 9x for the numerator. The rest is in the denominator. We have a negative exponent. It flips back down, so we have inverse sine of 9x squared here, times another square root of 1 minus 81x to the fourth. You could write it all as one square root, just making sure that you use parentheses appropriately around each of those two groups. After the inverses, we have to tackle relationships between other things that are not trig and what is the connection. What we're going to do to develop the idea is find the slope of our cube root graph at 8. F prime of x in general, cube root is a 1/3 power, x to the negative 2/3. The slope at 8 is 1/3 times, plug in 8, this means cube root it, which is a 2, square it to get 4, flip it to get 1/4. So the slope at 8 is 1/12. If we look at 8, that definitely looks like a slope of 1/12. That's pretty flat. Now the inverse function is x cubed. I'm going to find f inverse's derivative. Let's find f inverse's derivative first at x. I take the derivative of my polynomial, I get 3x squared. Then I want to find f inverse's derivative at 2. 2 squared is 4 times 3 is 12. Looking here at my graph, we can see a pretty steep slope, a slope of 12. Well, what's the connection on these points? So the point we originally had here was 8, 2 on the cube root graph. The corresponding point I analyzed was the point 2, 8. Well, what's the connection here is when you have inverses, the points, you switch them to find the corresponding points on the inverse. So you're switching x and y as that relationship. Well, if I looked at my derivatives, the first one had a slope of 1/12, and the next one had 12. What's the corresponding theory of what's going on? They are reciprocals. Analytically, if I take two functions that are truly inverses and compose them, the input value that you're putting into that composition is what the output is, and that will always work for your inverse functions from pre-calc. I'm going to take now, because I want to show the calculus, which is the derivative connection, I'm going to take the derivative of both sides. Chain rule says f prime of g of x times the derivative of the inside is the left-hand side's derivative. Derivative of x is 1. Since g is the inverse, how do I describe g's derivative? It is 1 divided by f prime of g of x. We got the triple flip going on here. We flip to create a reciprocal, flip back to the original function, flip back to the inverse, put in the input. Well, what do I mean by the triple flip? Let's take ours from above, which is function g, and we wanted to find its derivative at 2. Flip around, create a fraction, 1 over, flip back to the original's derivative with an input, flip back to g, and then keep the 2. So flip, 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 equals 1 over f's derivative at, what's g of 2? Well, we discovered that up here. At 2, we're at a height of 8. So we have f's derivative at 8 now. I go to the original function, and its derivative at 8 was 1/12. If I simplify, I get 12, which is what we said the derivative of the inverse should be. So now it's working out analytically as well. Making connections. I'd pause the video and try the first two parts before watching. F at 0. F at 0 is simply 4. F prime at 0 has to be done after finding the derivative. So I'm going to say f prime of x first, which is 5x to the fourth plus 18x to the second plus 3. Notice keeping the notation, identifying what we're finding. F's slope at 0 is going to end up being 3. F inverse of 4. Well, the connection from pre-calc is that if the x is 4 on the inverse, then it's the y on the original function. So then I should be flip-flopping the x and the y. So the x on the original goes to the y on the inverse. F inverse's derivative, this is that new concept. So to find the inverse's derivative, flip, create a fraction, 1 over, flip back to the original. I want its derivative at, flip back to my inverse at 4. This should get me the value of the derivative of the inverse. But if you're pretty savvy, you probably already know, go flip the corresponding point. But let's see if we get it. 1 over f's derivative at the inverse's value at 4, which we said was 0, and the derivative at 0 we set up above was 3. So there we go. F inverse's derivative at 8. So to find the inverse's derivative at 8, remember, flip, 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 create a fraction, 1 over, flip back to the original's derivative of, flip back to the inverse at 8. The triple flip. What I'm going to evaluate first is 1 over f prime at some value. Well, the x on the inverse becomes the y on the original. So I'm going to start off going 8 equals x to the 6th plus 5x to the 4th plus 2. If this is a non-calculator question, they are designed so that the numbers shouldn't be too bad, so you could figure out by plugging in x's. And in this case, if x is a 1, 2 plus 5 plus 1 gives me 8. Oops. So the x is 1 to yield the y of 8. Sorry about that. So I'm going to say find the inverse. So find the derivative at 1. Well, the derivative in general is 6x to the 5th plus 20x to the 3rd. The derivative then at 1 would be 6 plus 26, 20, getting ahead of myself, is equal to 26. So the answer to the derivative of the inverse is 1 over 26. Calculate where g is the inverse, the derivative of that inverse. G prime at 6. To get it, flip, flip, flip. 1 over, flip back to the original, its derivative at g, because I'm flipping back to the inverse, of 6. Equals 1 over input of x becomes y on the original. 6 equals x to the 3rd minus 4 over x. Pause to think what x value that is going to correspond to, and again thinking about x's. In this one it would be x is 2, so I'm finding f's derivative at 2. To find that, I'm going to take f's derivative at x in general, which is 3x squared. And this minus 4 over x, you can think of it as minus 4x to the negative 1. So its derivative is plus 4x to the negative 2. I want to find the derivative at 2, which is 12 plus 4 times 2 squared is 4. Flip it, we get 1/4. So we end up with 12 plus 1, which is 13 for the derivative at 2. Last page. I'm looking at this limit statement and saying it looks very, very familiar. What do we recognize it as? This is a setup to find a derivative. And where is it calculating the derivative at? The input value, well, this is the a plus h, and this is the a in that formula. So I want to know what is f's slope at 1/2. To find it, I'm going to first identify the function. The function is what is attached to the a plus h. It's an inverse cosine function. Then derivative of inverse cosine is -1 over the square root of 1 minus x squared. We want to find the derivative at 1/2. So I have -1 over square root of 1 minus 1/4. That turns into -1 over the square root of 3/4, which is -1 times the square root of 4/3, flipping, which is -2 over root 3, choice D. Last problem, make sure you grab your graphing calculator. Go to y1 and plug in our function. Make sure when you plug it in to do a sine squared that you are careful of, you have parentheses around your x, and then you have parentheses around the sine of x. Notice the grouping to be squared. All right, before we get to that, we're going to say the derivative of the inverse at 3, flip, 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 flip to create a fraction, 1 over flip back to the original, get its derivative, and then flip back to the inverse at 3. There's my setup. Well, the x value on the inverse is the y value on f of x. So off to the side, I'm going to say 3 equals x over 2 plus sine squared x. I think it's easier to find a zero of a function rather than an intersecting of curves. So I always slide my numbers over to create a zero. Make sure your graph is in radian mode. To do that, you're in your home screen, hit mode. Make sure radian is highlighted, not degree. And then to graph this one, I'm going to use a trig window. So I'm going to hit zoom 7 so it will graph it as a trig window because I'm dealing with trig. If I need to adjust it, I'll adjust it. I can see right here I've got the zero of the function. I'm good to go. Second, trace to get calculating zero of the function, number 2. Left bound, scooting over until I'm really close to my zero of the function, but don't go over the line. So I'm going to hit enter for the first one, left bound. Right bound, I got to make sure I definitely cross. I'm definitely crossed. I hit enter, and the guess, we hit enter. The value for this is 4.3086. But that keeps going on and on. So I want to make sure as I progress through the problem, when I go here, I say 1 over f's derivative at 4.3086. But I don't want to chop it off at that because I'll lose value. What we do is we come here to the calculator, hit second quit, take a look at x, and that should be stored in. There's that value stored. What I need to find next is f's derivative in general. X over 2 is like 1/2 x, so the derivative to start is 1/2. Chain rule here, plus 2 sine x cosine x. Going back to the home screen, I'm going to type in my derivative, 0.5 plus 2 sine x. And remember, it knows what x is, cosine x. It will retain the value from before. I get 1.2225, so it's 1 divided by 1.2225. But again, it's not 2225, it's a rounded answer. So I'm going to, actually let me erase all these equal signs because this is a rounded value and I don't want to say that those are specifically equal. So I'm just going to traipse my work down here. And when I get to the inverse at 3 at the very end, this is where we have to have at least 3 place decimal accuracy. So by erasing those, I'm not saying that they're all equal because technically they're not. I'm just showing the work and the thought process. And I'm going to say 1 divided by second answer. And my end answer for this one is 0.818 for 3 place decimal accuracy. And that's it for 3-7, day 2.